Hello, I'm Ankit Manerikar, and I will be speaking for the next few minutes on my project for the course BME 595, which is titled Indoor Place Categorization for Visual SLAM. As the title suggests, this project mainly focuses on applying deep learning techniques for the purpose of extending visual place categorization to vision-based SLAM systems. As you may know, the concept of SLAM, or simultaneous localization and mapping, is instrumental for autonomous navigation, as it establishes a stochastic framework that not only allows a robot to map an environment but also localize it itself in the same simultaneously. In modern context, vision-based SLAM systems are crucial for constructing high-quality indoor and outdoor maps for applications such as indoor autonomous driving and aerial surveying. On the other hand, visual place categorization is a problem in image classification that is very well addressed by the deep learning community. Basically, the problem of VPC comprises of assigning a scene attribute to a given image, that is, assigning a label from a predetermined set of labels to a given image that closely corresponds to the scene that the image is representing. The problem of VPC is fairly straightforward in case of 2D images. However, it may not be as straightforward for extension to SLAM. This is because the problem of VPC for indoor maps generated by SLAM comprises of assigning scene attributes to different sections of these 2D or 3D indoor maps that may be generated from SLAM, even though these maps are basically generated from an input stream of 2D input images. Uh, uh, what also adds to this is the fact that this stream of input 2D images from which these indoor maps are constructed from are highly spatiotemporally correlated, which is a fact that may not be explored if the scene labels for these individual raw images are simply propagated to different sections of the map. VPC to visual SLAM. The two-tier classification technique involves cascading two classifiers back to back for the purpose of implementing VPC. Here, the first classifier is a CNN that is trained on an indoor place recognition dataset for 2D images and operates on the input stream of images that are fed to SLAM. Because these images corresponds to different robot pose estimates as it propagates for SLAM operation, at the end of the SLAM operation, uh, the output of the CNN generates a spatial grid of scene labels that correspond to the indoor map. This spatial grid of labels is then fed as input to the second classifier, which is basically a clustering classifier that explores the spatial correlation between these different scene labels and therefore generates a consistently labeled indoor map wherein different sections of the indoor map are labeled by appropriate scene categories. For the purpose of implementation of this two-tier classifier, um, we first consider the primary classifier, which is the VPC CNN. In order to train this CNN, we have selected the Places 365 dataset uh, for place recognition, which is maintained by MIT. It is an image data set that comprises of nearly 1.5 million images with 365 indoor and outdoor scene categories and 5,000 images within each scene category. Since this project deals with only indoor scene categorization, we only choose 50 indoor scene categories out of the entire category set for the purpose of training the CNN classifier. Um, a number of off-the-shelf CNNs are available for that are trained on the Places 365 dataset. From these CNNs, we have chosen the ResNet 18 CNN for the purpose of implementing a two-tier classifier. For training the CNN, we have retrained the last fully connected layer of this ResNet using the 50 indoor scene categories for the purpose of VBC. The training operation is performed using with 10 epochs with a batch size of 50 and using an ADA-grade optimizer with a learning rate of 0.1. The second classifier, which is the clustering classifier, implements a 2D agglomerative clustering algorithm for the purpose of clustering the scene labels. Here the feature space is nothing but the spatial coordinates of the individual scene labels. Of implementing the primary classifier for the two-tier structure, we considered the different off-the-shelf CNNs that were available and were trained on the Places 365 dataset and tested them for the validation accuracy for the corresponding indoor scene labels that we have, scene categories that we have selected. As you can see, out of the different CNNs tested, ResNet 18 gave the optimum performance in case of validation accuracy and hence was selected for implementing the CNN, the two-tier classifier. The architecture of the implemented CNN is illustrated in this slide. As you can see, the traditional ResNet 18 CNN architecture is modified by replacing the last fully connected layer by another fully connected layer of 5 and 2 into 50 dimensions of this dimension and retaining this fully connected classifier on the reduced indoor scene categories. Following this layer, an agglomerative clustering classifier was cascaded, which clustered together different scene labels spatially and therefore generated the final labeled indoor map. These are the training results of the implemented CNN. As you can see, the training of the CNN for 10 epochs results in a training and cross-validation accuracy of nearly 85 to 87%, which is a good value for operation. We trained the CNN using both the SGD optimizer and the ADA-grade optimizer. ADA-grade optimizer showed a better conversions, reaching a accuracy of 76% in the first epoch itself, and hence was chosen for later operations or the final implementation. Final two-tier classifier. We made use of the RVL dataset, which consists of SLAM reconstructions of the EE, the MSEE, and physics buildings at the Purdue University. And here the entire system in action. As you can see, the CNN generates these output scene labels for the individual input stereo images that are fed to SLAM. The agglomerative clustering classifier clusters together these labels and generates distinctive scene labels for different sections of the map, and thereby the entire operation is continued along. You can check the entire video in the link description. Hence, I'll skip to the next slide. This is the entire map reconstructed from the SLAM operation. The first image in this slide is the original point cloud, which does not contain any scene labels from the CNN. The second image in this slide is the labeled indoor map, that uses the pre-trained ResNet 18 CNN without being retrained on the indoor scene categories themselves. As you can see, because the pre-trained CNN operates on this indoor map, the output is quite cluttered in places because of being mislabeled as an outdoor scene. Concluding this presentation, I'd like to say that the two-tier technique for VPC in visual SLAM allows for a faster scene categorization for SLAM compared to the segmentations of the point clouds extracted from this indoor map, which is a much more expensive task than simply labeling the input stream of images and clustering them together. Of course, the quality of this partition map depends upon the performance of the secondary classifier, which is the clustering classifier, and therefore can be improved by use of more sophisticated clustering algorithms. Um, Hence, the future possibilities of this system is to implement more sophisticated algorithms for exploring the spatial-temporal correlation, as well as extending the same to multi-sensor SLAM for indoor map building. Thank you.